Welcome to the GeoDict session 2 here at the IBSim 2020 conference. I will talk about geometry analysis and material properties in GeoDict 2021. My name is Sebastian Rief and I work as application engineer at Math to Market. And now I will dive directly into the topic. Here are the slides that you have. They contain very much information, too much information or more information than I will cover now in those sessions. But you can use all the information here to do the workshop again for yourself and even do a bit more than I will show you here. So let's move on quickly. Here you see the splash screen of GeoDict. You saw it already before in the first session, so I will not talk too much about that now. But now start with the second session, setting up GeoDict correctly and getting started. So the first thing you have to do is set up your project folder. For this, you just have to take the project folder that we deliver to you. Here the folder is called Workshop Project Folder. You can keep that name or change it, but in principle it doesn't matter. And this folder at the beginning only contains one file, which is a GeoDict structure. So just make sure that this folder is selected in GeoDict. You can see, or you can check that here with the Choose Project Folder button. Click on that and click on Select Project Folder and navigate to your project folder, and then you're set. In GeoDict, everything you do in your current session is saved in the project folder, all files, all simulations, and everything. So you just have to keep this folder and have all information that you need. So then let's open the structure. You can do this either here over File, Open Structure, or with the icon here. Click on the icon, select the one structure that is in there, and open it. Now you directly start in the 2D view. We will directly switch to the 3D view. How to navigate in here, there's more on the slides, but the session is not too long now, so I will just jump over this. Therefore, we just switch to the 3D rendering up here. Click on the button for the 3D rendering. And well, directly you see the structure from above, or you don't see that much because the perspective is just from the top and the renderer is not yet set up correctly to view enough here. So you can rotate the structure with left clicking and dragging the mouse. You can zoom with the right mouse button or just with the mouse wheel, and you can pan the structure with holding the middle mouse button or the mouse wheel and moving the mouse. So then I will change the renderer for the structure. So click up here on structure, and then you select several renderers. The renderers we use mostly are the box renderer or the smooth renderer. The box renderer, as you can see, if you zoom very deep in, shows the voxel structure. So that's the structure you're working on. And sometimes for simulations, it's very helpful to just see the voxels because that's just the material you're working with. But the smooth renderer just looks a bit nicer. So I switch over to the smooth renderer. And here you can see the lighting is a bit better. The surfaces are smooth there. So, well, it's just a bit more appealing. Then here under the camera tab, you have some more options. I will enable here the show halo option. Well, it's just a bit more appealing. If you want to make really nice screenshots, you can switch on the global lighting here. Then a global lighting map is calculated for the whole structure. But as you can see, for each structure, this just takes time. And therefore, I mostly don't use it when I'm working in GeoDict, and I only use it for screenshots. So I will also disable this again. Then we'll just change the color for the structure, because this is here a material in a electrode structure and it's a bit unrealistic that it's red. So you can click up here on the color and visibility settings, click on the icon, and then we can see here we have at the moment two material IDs in the structure. ID 0 is invisible, it's here the pore space between the grains, and ID 1 is in red, so we want to change the color for material ID 1. So you just have to click on the color here, and then you get a color picker, and I will switch here to light gray, and it changes immediately, and then you're set and have the structure in here. Well, we can jump a bit in here, load the structure, we did this, we did this. Yeah, one of the first things that you perhaps want to do is to save screenshots. It's quite easy in here. You can simply click here on the Save Image As button. Here, don't wonder if this window looked a bit weird. That's just because I'm using a special preliminary version here of GeoDict. Don't mind, in your version this won't happen and the window will directly open in the correct size. So you can choose resolutions how you want. I will just keep the current resolution. You don't have to change anything here. Just click OK and select a name for your structure. Save that, and well, then you're set. And as you can see in the project folder, then you have here just a picture or PNG file for your structure. So yeah, I think this part you learned also yesterday, that GeoDict is organized in modules, and yesterday you did most of the things, you spent most of the time in the import and model tabs here, and I will show you now something about the analyze and predict tabs. So the first thing we will start with here with perodict under the analyze tab. Just check the slides that I'm in the right pace. Yeah, I think I can also jump over this. So then let's directly start with the work here. The first part here will be about geometry analysis. So we analyze the pore space in the structure and we analyze the grains in the structure. And as in the screenshot you can see here is just a nice screenshot. Is not of the structure that we investigate now, but it's just a nice example of what you can do in GeoDict. The complete visualization is done in GeoDict, and what you can see is a visualization of the pore sizes in this granular structure here. We will analyze the pores with two different algorithms. One algorithm is granulometry and the other one is porosimetry. In principle, granulometry is a geometric analysis. So in principle, you take the pore space, or you take in a 3D image of the pore space, and then you fit spheres into the pore space. And to each point in your pore space, you assign the size of the largest spheres that contains this point. So as you can see here, the orange area is all the area where the largest sphere fits in here. In opposite to that, there is also porosymmetry. It's a bit more unintuitive in the beginning, but it's just a measurement method, how you can measure pore sizes or pores in a structure without having, for example, a CT scan or without cutting the structure into parts. There exist measurement devices which measure the pore space by pushing a fluid into the structure, and then you can measure the pressure you need to push the fluid in there, and with that pressure you can calculate the size of the pore throat. So the well the size of the pore throat, so the size of the way to the pores, if you want. So the point is that in that case you don't get the here, for example, you don't get a number for a very large pore because the ways to that pore are smaller than the pore itself was. So what we do here in the algorithm is that we push in spheres, so from the outside of the structure, and we always look what is the largest sphere that we can push in here. So the sphere here that you can push in here is smaller than the sphere you can push in here. So then it's quite easy to do such an analysis here in GeoDict. So you just select and analyze perodict, and then the first one we will do is the porosymmetry. Click here on pore size distribution porosymmetry. Then, as in all GeoDict modules, you can get to the settings for the algorithm with the edit button. Click on the edit button. We will not change much in here. Here you can see the basis of the algorithm. So in the reality, you just have to select from which sides of your structure you push in the fluid. Well, here for this example, we select all sides. In reality, that wouldn't work because, well, you just have to leave some sides free here. But in this way, we can just measure it from all sides. And what we select too is here write pore size distribution as a GSD file, which just means that you write the pore size distribution in a format that you can visualize later. Just click OK, and then the next thing is just click Run and wait until the algorithm is finished. Well, what you can see here, there are always remaining times that are estimated, but I think you know that for every algorithm it's always a bit difficult to really estimate the time. That's why this is changing a bit here, but it shouldn't take too long. Usually it should not take much longer than a minute here, and it will be finished soon. So there we go. For every simulation or every structure generation, as you saw already yesterday, GeoDict creates a result file, and after the analysis or the simulation, this result file is open in the result viewer. And well, usually you have a results report in there where the most important results are reported. For example, your characteristic diameters and much more information. Then here in this example, you have also some plots, so you can visualize the volume fraction over the pore throat diameter, and you get also a cumulative plot for that. And then you have the map. It looks a bit complicated, but this just contains all results you have in simple tables. And you can use this information either in Microsoft Excel later, or directly from GeoDict. You can use Python to use those results and do further analysis with that, or do further simulations based on the information from that. Then I just told you that we should select the pore size distribution to be saved. If you don't select that, then this button here is also grayed out, and you can't open it because it's not there. Now we can click on this load GeoDict size distribution and just confirm the next dialog, and then the pore size distribution is loaded in here. I will just quickly switch to the slides. So here on the slides is just a bit more information about the saving plots, for example, and about the maps. I will just jump over that now. Here you can see the visualization that we just made some seconds ago. And on this slides, on this slide is explained how you can disable the visibility of your structure. I think that's quite nice if you want to see the pore space. So let's switch back to GeoDict. Here you see the structure with the pore space, and then you can simply disable the structure here by just checking the box here. And what now happens, one thing we have to make sure that it's selected here under the volume field tab. You can select where in the structure your volume field is visible. So now if I re-enable this, you see the volume field is also shown where the structure is, and in those places it's just blue because the pore size is 0 there where the structure is. And if we disable it again, then you can see that the volume field is also not shown in those places. Back to the slides. Here the part about saving the video, I will jump over that. If you want to go through that on your own, it's quite easy. Everything is explained in the slides. But additionally, we will have another section about, or another session about visualization. And in this session, those things are explained in more detail. So I think it's okay if we jump over this here. It's just that you see you can save videos, and they are quite nice. Well, but I think that I don't need to go into in more detail in here. So now let's switch to the other algorithm, to the granulometry approach. Starting this analysis, it's just an analog to the porosymmetry. Change here to, or select the pore size distribution granulometry under perodict. Click the edit button again. Then here the boundary conditions are perfect. We can just keep them. You can, for example, also select periodic boundary conditions if your structure is periodic in reality, but since this is a CT scan of a real structure here, it's not periodic, so it's more meaningful to use symmetric boundary conditions. And again, if we want to visualize the structure or the result, we have to select the right pore size distribution as GSD file. Click OK, click Run. Wait some time, and then you get the result for this analysis too. I believe it should be a bit faster than the porosymmetry because the algorithm is more simple. Let's just see if I'm right here. Yes, I was right. And then it works the same way here. You get a result file with all the information, and you have to get similar information here. What is quite interesting in GeoDict that you can use the result viewer to compare the results. You just have to select both or multiple results file up here. So just hold Shift and select the files that you want to see. And then you have like two result viewers at a side. Then you can, for example, disable here the post-processing options here by holding here the line in between and just dragging it over to the side. And then you can, for example, compare the results. You can see both plots on side by side. And for example, as we can see here, the volume fractions here are a bit different on the axis. So it's better if we select if we set the axis in both plots that they show the same numbers. You can right-click here on the graph settings or the plot settings. Right-click on the plot and then click on Edit Plot Settings. Then you get some settings here, and you can disable the automatic scaling for the y-axis, and we just change it to 0 to 30. Click Apply, and well, then it automatically enables here the plot option. We don't want to see them here. Do the same for the other plot. Apply, close it again, and then you get both plots with the same axis, and then you can compare them better. You can also combine the plots directly in one plot. This is here with the combine results option. We well, I can simply show it here. Just click on combine results. If you have selected multiple results files, then you have some more options here. We can keep it by default here. And then, for example, or in this example, you get then a combination of the plots. So you get the volume fraction. What is a bit wrong here is clearly that one analysis, the granulometry, measured the pore sizes, and the other algorithms, the porosymmetry, measured the pore throat sizes. So we have other values here on the axis, but well, GeoDict just has to select one of the titles here, and the first one was selected, which was pore throat diameter. But if you compare results of the same analysis, just of different structures, then it makes again a bit more sense than this comparison. But even here you can compare the volume fractions. So close the result view, or close all files in here. Let's have a look on the slides. So we just did all those parts here about the result files. And now to the next interesting point, that we now want to analyze the grains in the structure. I will just disable the visualization of the volume field here, because it might be a bit misleading, because we only want to see the structure. You can either disable it here, and you can also completely discard the file from memory. If you go here on File and Discard Volume Field, then it is deleted from memory, and well, it doesn't disturb you anymore in there. So we'll check that I select the right parameters in GrainGeo, or in GrainFind. For GrainFind, you also find it under the Analyze tab up here. Click on Analyze and then GrainFind. Then we select here Identify Grains. Here in GeoDict 2021, we have also an option to use an artificial intelligence algorithm for identifying binder in structures, just to mention this. But now we want to identify the grains in here. Click again, Edit for the options. And then I just want to make sure that I select the same settings that we are mentioned in the slides. So yeah, here for the minimal grain diameter, we select 4 voxels and the interface threshold to 16. This sounds a bit like magic numbers. It depends on the structure that you analyze, and sometimes you have to do a bit try and error which parameters work best. In principle, with the minimal grain diameter, you select the smallest grains that are used in your analysis, and if a grain is smaller than that and is somewhere floating in space, then it's just discarded and not analyzed. And if it's connected to a larger grain or larger structure, then this part is just combined with a larger structure. And similar, you have the grain fragment reconnection here. In principle, the whole algorithm here in grain find is based on a watershed algorithm, and it just makes a segmentation into different grains. And it might happen that it this is a bit over segmented, so you get more grains than you should have, and then you can use that reconnect grains algorithm. It just checks the sizes of grains which are connected and compares those sizes to the interface they share, and based on this information, those grains are then reconnected again. Then here we keep the option to remove grain fragments at domain boundary. You can just imagine if you have a structure like this, and you have here some half grains here at the boundary, and you analyze them, then you might get a bit wrong information about the grains because well, those cut grains are not really representative, so you can tell a grain find to simply discard them. So then click on OK, and click on Run for the analysis. And I will just start the solver, and then I think we can directly start in the break and go further than in the next part. So if you have any questions, then just feel free to ask now. And I just click on Run to run the solver, but we just yes.